the most important but the most incompletely understood concept in all of science. This most important concept in all of science is nothing but entropy, symbolized as capital S, a property that the German scientist Rudolf Clausius postulated to exist in nature in 1865. He used it to formulate his mathematical statement of the second law of thermodynamics, namely, delta S total is always greater than or equal to 0, where delta S total is the total change in entropy of the system and surroundings in question. That is, the total entropy always increases in any spontaneous process, never ever decreases. In other words, delta S total is always greater than 0 for all spontaneous processes, never less than 0. And it does not change once the total entropy reaches the maximum possible value under the given conditions. This maximum corresponds to the equilibrium state, and hence delta S total always equals 0 for all equilibrium states. Hence, the two parts in the mathematical statement of the second law. He defined delta S system as Q reversible over T for an isothermal process, namely a process in which the temperature is kept constant. When the temperature changes, one has to resort to calculus. ds is defined as d/q reversible over t, and delta S is the corresponding definite integral from the initial temperature to the final temperature. Now, a brief history of science is in order here. In his 1850 paper titled "On the Motive Power of Heat and on the Laws which can be deduced from it for the Theory of Heat," Clausius stated the verbal statement of the second law as heat always naturally flows from hot to cold. He was not satisfied with this innocuous sounding statement. In comparison with the elegant one for the first law that he published in the same paper, namely, energy of the universe is conserved, meaning it always stays constant and can neither be created from nothing nor be destroyed into nothing. Since a law indicates in the form of a succinct mathematical statement the numerical quantitative pattern that one recognizes to exist in a large enough amount of relevant experimental data after an appropriate arithmetical, graphical, theoretical, etc. type of analysis of the data, he was even more dissatisfied with the lack of a mathematical statement for the second law in comparison with the deceptively simple and a classic first law statement of delta U equals Q plus W. Therefore, he started to perform a theoretical analysis of the relevant experimental data to see if he could identify any numerical quantitative pattern that might exist hidden in the data. As a result, in 1854, 4 years later, he published another paper titled On a Different Form of the Second Law of Thermodynamics, where he introduced what he called a mysterious ratio, Q over T, heat over Kelvin temperature ratio. It was mysterious to him then because he couldn't realize its significance until later. In the 1854 paper, he stated that heat over Kelvin temperature ratio increases in any irreversible or spontaneous process, while it is constant in any reversible process or equilibrium state. In the 1865 paper titled On Various Forms of the Laws of Thermodynamics That Are Convenient for Applications, he identified that mysterious ratio as change in entropy and gave the mathematical statement of the second law as delta S total is greater than or equal to 0. He also made the elegant and succinct verbal statement of the second law that the entropy of the universe is increasing since it is an isolated system, thus probably replacing his dissatisfaction in 1850 with complete satisfaction and joy. In part 3 of this video series, I will show a possible example theoretical analysis along the lines of Clausius that will illustrate a possible origin of the second law mathematical statement and the idea that entropy always increases during any spontaneous process and reaches the maximum possible value at the corresponding equilibrium state. The second law of thermo is known to govern all processes in nature without any exception, whether it is a physical or chemical or biological or geological process. To this second, we don't know of any process that violates this law. In other words, we don't know of any spontaneous process in which the total entropy of the system and its surroundings decreases. What the famous British physicist and writer C.P. Snow said a good many times regarding his frustrating experience in gatherings of non-scientists that were thought to be highly educated will drive the point home here. He said, asking them to describe the second law of thermodynamics was nearly the scientific equivalent of asking if they had read the work of Shakespeare's, and yet they couldn't describe it. In other words, he implied that anyone, not even in the scientific field, knowing the second law is as significant as every British knowing the work of Shakespeare's. Thus, it is the most important law of nature, and hence the property of entropy underlying it can be dubbed as the most important concept in all of science. Although Clausius felt compelled to postulate entropy as a vital property existing in nature, as the result of his theoretical analysis of the experimental data, which he desired to explain and understand, he could not figure out what exactly that property represented. He and others could only calculate the changes in entropy occurring in various systems during various processes using the heat over Kelvin temperature ratio. They could not explain, could not understand why they occurred the way they did until more than 15 years later, when a possible interpretation of entropy was attempted for the first time. At about the same time as the above thermodynamic theory, another theory was also evolving. It was kinetic theory of matter. It postulated that all matter is made of tiny invisible particles, that particles of matter are in constant motion all the time, and that temperature is a measure of the average kinetic energy of motion of particles. It also assumed that the particles are held together by an attractive force, and that the particular physical state of a given substance at any given temperature and pressure is simply the result of which one of the two wins, namely particle motion or particle attraction. Postulate is simply a statement that is assumed to be true without our knowing if it is actually true or not. A theory is simply a collection of such postulates. It is to be contrasted with any fact, which is a statement that summarizes the observation we make. The one and only function of a theory is always to help us make sense of, understand, explain facts. See my video series on scientific method for a thorough understanding, and also my book Understanding Chemistry by Using Scientific Method as a Unifying Thread. Chemistry happens to abound in theories. In this book of mine, one will see the postulates of all theories relevant to chemistry. And the book refers to these postulates constantly to help one understand and explain the various facts in chemistry. One will also get to understand thoroughly the origin of various laws in terms of the relevant experimental data with the corresponding analysis and the resulting numerical patterns illustrated. Then the difference between laws and principles, the factual basis for various empirical classifications, the rules behind the proper use of various scientific representations, etc. Much more importantly, the book shows how these various components of scientific method serve as a powerful unifying thread to connect and thus understand and remember the various aspects of chemistry, which is its major objective. The video series on scientific method will be forthcoming. Kinetic theory of matter imagined the particles in a solid to be closely packed together in an orderly arrangement held together by strong attractive force. The particles executing only vibrational motion. As the solid is heated, the average kinetic energy increases according to the theory, and the particles move more and more vigorously. At one point of time, the vigorous motion is able to overcome the attractive force, and the particles move away from one another considerably, resulting in the liquid state. Here, the particles execute short-range translational motion, and they happen to be disorderly somewhat. As the liquid state is heated, the vigorousness of motion increases even further, and at one point of time, they overcome the attraction and move much farther away, leading to the gaseous state. Here, they execute long-range translational motion, and they end up being very disorderly. Thus, the term disorder of particles got to be associated with liquids and gases, while orderly arrangement of particles with solids. In 1882, Hermann von Helmholtz interpreted entropy as a measure of the disorder of particles. This was the first physical idea that arose regarding entropy. It is known that entropy increases as we go from the solid to the liquid to the gaseous state of any given substance. For example, the standard molar entropy at 298 Kelvin in the unit joule per Kelvin mole is for ice 38, for liquid water 70, and for steam 189. According to kinetic theory of matter, as we saw earlier, disorder also increases as we go from the solid to the liquid to the gaseous state. Thus, Helmholtz's interpretation of entropy as a measure of disorder of particles correctly explains this observation regarding the entropy of the physical states. Today, we often hear entropy as being simply interpreted as disorder, not as disorder of particles. This omission of particles is completely wrong. Entropy is a property we need to keep in mind, whose value is always determined by a collection of particles. This omission has led to wrong applications in the macroscopic world, as evidenced in Mark Thompson's 2015 New Yorker cartoon of a child's exceedingly messy room, for which he blames entropy to his mom, who enters the room and looks at the mess. No matter how the items in that child's room are arranged in space, whether orderly or disorderly, their volume and temperature remain the same. Therefore, the distribution of particles in space inside any item remains the same, since, as we will see in part 2 of this video series, only a change in volume can affect their spatial distribution that leads to positional or configurational entropy. There energy level distribution also remains the same, since, as we will soon see in this part, only a change in temperature can bring about a change in their energy level distribution that leads to thermal entropy. And only if either or both of these two kinds of distribution of particles change, a change in entropy can ever occur. It can never ever occur just by changing the orderly arrangement of items into a disorderly one in the macroscopic world. Several textbooks and websites make the same blunder. They say, for example, a shuffled collection of red and green marbles in a beaker is of higher entropy than a layer of, say, red marbles above which there is the layer of green marbles. Obviously, the former is more disorderly than the latter at the macroscopic level, but the particle distribution is the same in both at the microscopic level. Or they wrongly say a new deck of cards possesses lower entropy than when the deck is shuffled. And at the end of the chapter, they ask the question, which possesses higher entropy? Shuffled bricks lying on the ground or the wall constructed using those bricks, wrongly expecting the answer to be the former. In each of these cases, the total entropy remains the same, is something to be understood. A fundamental mistake that those who oppose the idea of disorder, Frank Lambert being generally considered the strongest opponent, impose on themselves is that they use the wrong interpretation that entropy is a measure of just disorder omitting of particles completely, without realizing that theirs is a wrong idea itself. They venture into opposing it. As a result, those who correctly understand that the increase in entropy from solid to liquid to gaseous states of any given substance is due to an increase in the degree of disorder of their particles, are obviously confused as to why the opposition even exists. And in the case of biology, the small molecules, water and carbon dioxide, combine to form much bigger and more structured sugar molecules during the photosynthesis by plants. Proteins are formed by the folding of their polypeptide chains comprising amino acid residues. Those who correctly understand the resulting decrease in entropy as due to an increase in the degree of order of the concerned particles also wonder why the opposition exists. The question arises when they don't recognize that the opposition is simply the consequence of the omission of particles in these opponents' own definition of entropy. Hoping that clarity will grow after watching this video that the interpretation of entropy as a measure of disorder is wrong, but its interpretation as a measure of disorder of particles is indeed correct, although, as we will see next, the latter is simply incomplete. Yes, after Helmholtz's interpretation, several experimental facts accumulated regarding changes in entropy during processes which could not be explained, understood in terms of disorder of particles. It had to be realized that entropy must be much deeper than disorder of particles at the microscopic level. What is it actually? In 1877, Ludwig Boltzmann wrote a 50-page paper where he showed how one could calculate the probability of finding particles of a sample of matter in different energy states. In 1896, he wrote another paper in which he made a mathematical connection between entropy and the above probability. In 1900, Max Planck modified that equation slightly and gave us the equation S equals K log W. The currently used one is S equals K ln W, where the common logarithm has been replaced with natural logarithm. Planck gave K the name Boltzmann constant to honor the latter. In this equation, W represents the number of possible ways in which the particles of a given sample of matter can realize or exist in the macro state it is in. Each possible way is referred to as a microstate as opposed to the macro state. Thus, W is equal to the number of possible microstates. According to Boltzmann, a given macrostate at the macroscopic level of substances is always made up of a specific number of microstates at the microscopic level of particles. Today, S equals K ln W has become an extremely powerful equation that precisely interprets what entropy actually might be, shedding a complete light on entropy and giving us a deep insight into it. In the absence of this great contribution by Boltzmann, we might still have only an incomplete understanding of entropy. Although Boltzmann took a classical approach to his equation, today one finds it much more convenient to use the results of quantum theory in order to appreciate the use of W in the above Boltzmann entropy equation. This is the approach I will take in this part to illustrate the use of that equation in understanding entropy thoroughly. To illustrate using the equation, let us consider a piece of metal that is made of just 3 atoms to keep the analysis simple enough. Recall that in any solid, the particles execute only vibrational motion, such as the pendulum in a grandfather's clock does. According to quantum theory, the particles can vibrate using only certain allowed vibrational energies. If we assume simple harmonic motion, these energies are given by the equation given to us by quantum theory. E sub v equals v plus 1/2 times h nu, where v is vibrational quantum number, h is Planck's constant, and nu is the frequency with which the particles vibrate. V is allowed to assume only the integer values 0, 1, 2, etc. all the way to infinity. Therefore, the allowed energies are 1/2 h nu, 3/2 h nu, 5/2 h nu, etc., with the gap between adjacent vibrational energy levels being h nu. H nu is referred to as one quantum of vibrational energy. To make the math simpler, it is generally assumed that E0 equals 0 instead of 1/2 h nu. Therefore, the allowed energies become 0 h nu, 2 h nu, 3 h nu, etc. This is what we will be using in this discussion. At absolute zero of temperature, all the particles making up a solid are at the lowest allowed vibrational level, V equal to 0. That is, they vibrate with the lowest allowed amount of vibrational energy. E0 is equal to 1/2 h nu. Yes, it is a widely prevalent misconception that the particles of the solid stop moving completely at absolute zero. No, they don't, according to quantum theory. Thus, the three atoms making up our tiny sample are at the V equals 0 level. There is only one way in which this energy state can be realized by those particles. This will become clearer when we consider the next scenario. Thus, W equals 1 for this energy level distribution, since in Bottzmann entropy equation, W represents the number of ways in which the system can realize or exist in the macro state it is in. Incidentally, the third law of thermodynamics states that the entropy of a pure and perfect crystalline solid at absolute zero is 0. The explanation for this is as follows. Since W equals 1 for the energy level distribution of the particles of the solid, the resulting thermal entropy equals 0. When the solid is a pure, perfect, crystalline one, there is only one way in which a perfectly orderly arrangement of the constituent particles of only one kind can ever be realized. Therefore, W equals 1 and the resulting positional entropy is also 0, yielding a value of 0 for the total of both kinds of entropy. Let us now say the solid absorbs 3 quanta of vibrational energy from the surroundings. That is, it gets heated and the temperature rises. It does not matter for our purposes here what the resulting temperature is. What is important is that the temperature is now higher. In how many ways can this absorption of 3 quanta occur? Is an important question that needs to be considered in this Bottzmann analysis. The answer has to do with a math concept called partitioning. In how many ways can we partition or split the integer 3? In 3 ways, namely 3, 2 plus 1, 1 plus 1 plus 1. Each number here is taken to represent the number of quanta absorbed by one particle. Thus, one particle absorbing all 3 quanta is one way, one particle absorbing 2 quanta and another 1 quantum is the second way. Each particle absorbing 1 quantum is the third and last way. No other way is possible at all. Each of these 3 ways is referred to as a possible energy level distribution of the particles in question. We have represented these as D1, D2, and D3. Any given integer can always be partitioned in a specific number of ways. One should employ the corresponding strategy for any given total number of quanta absorbed. The next question to consider is, in how many ways can each of these distributions occur? In other words, how many microstates are possible for each possible distribution, and hence what is the total number of microstates possible for the given macrostate, which is, in our example, n equal to 3 atoms and U equal to 3 quanta at the temperature T1. That is, what is Wi for the ith distribution and what is W total equal to sigma Wi. To carry out this analysis, let us label the 3 atoms in the solid as A, B, and C. In the case of D1, the atom absorbing all 3 quanta can be A or B or C. Thus, there are 3 ways in which D1 can occur at the microscopic level. Each of these 3 ways is called a microstate. Microstates make up a macrostate. Therefore, W1 corresponding to D1 equals 3. For D2, the atom absorbing 2 quanta can be A or B or C, and that absorbing 1 quantum can be either of the remaining 2. Thus, there are 3 times 2 equals 6 possible microstates, and they are shown here. Notice that AB and BA are distinct ways when A and B occupy different levels. But AB and BA both would represent only one way when A and B occupy the same level. In the latter case, the description is the same for both, namely that both A and B occupy that one given level. In the case of D3, since AB and C are all in the same level, V equals 1, there is only one way and W3 equals 1. That is, in this case, ABC, BAC, CBA, etc. all result in the same description, namely that all three occupy V equals 1 level. In a similar manner, at absolute zero that we looked at earlier, there is only one way in which all three atoms can be at V equals 0 level in that case. That is, the number of possible microstates is only one, and hence W equals 1. Thus, at absolute zero, the entropy S equals K ln 1, which equals in turn 0 as mentioned earlier. Therefore, when n equals 3 and the internal energy U equals 3 quanta, W total is equal to W1 plus W2 plus W3 equal to 10. And S equals K ln 10 equals 2.303 K. Thus, when the solid absorbs 3 quanta, its entropy increases from 0 at absolute 0 to 2.303 K at the new higher temperature. At any given moment, the solid is in one of these 10 microstates, constantly changing among them. It changes from one microstate to another through collisions among the atoms and the resulting exchanges of energy. For example, at a given instant, let us say the solid is in microstate 2 of D1, in which particle B possesses 3 quanta, with A and C both being at the lowest energy level. Atom A now collides with B and absorbs 1 quantum, leaving B with 2 quanta. The result is microstate 6 of D2 that we saw earlier. In this manner, constantly the microstates keep changing, but the system with n equals 3 is always in the same macrostate of internal energy U equal to 3 quanta. All 10 microstates correspond to the same macrostate, and thus there are 10 ways in which the system can exist in this particular macrostate. That W and hence S increase as T increases is observed to be a general trend in nature, as also illustrated by the same solid absorbing 4 quanta this time, leading to a still higher temperature. The same kind of Bottzmann analysis can be performed in this case also. Integer 4 can be partitioned in 5 ways, namely 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. The last choice requires 4 particles, and this possibility is not an actuality in our case of n equal to 3. The first 4 result in 4 possible energy level distributions, D1 through D4. In this case, it is easy to draw the microstates and figure the value of W in the case of each distribution. When the number of particles and the energy involved are considerably large, conceptually figuring the number of microstates is very difficult, nay, even impossible. A chapter in math titled Permutations and Combinations comes to our rescue here. Accordingly, W equals n factorial divided by n0 factorial times n1 factorial times n2 factorial, etc., all the way to n sub n factorial, where n is the total number of particles in the sample of matter in question. N0, the number of particles at E0 level. N1, the number of particles at E1 level, etc. N sub n represents the number of particles at the highest occupied level. It is not necessary to include the unoccupied levels here, the reason for which will become clear soon. The symbol for exclamation mark represents the factorial of an integer. For example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, and 8 factorial equals 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 0 factorial happens to equal 1. And hence, there is no need to consider the unoccupied levels for which the number of particles is equal to 0. In the above case of U equal to 4 quanta, either by conceptually drawing or by applying the equation for W, it can be seen that W1 equal to W3 equal to W4 equal to 3, and W2 is equal to 6. Therefore, W total equals 15 and S equals KLN 15 equal to 2.708K. This is higher than that when 3 quanta were absorbed. Thus, as the temperature increases, higher and higher energy levels get occupied at the cost of the population at the lowest energy level, and W and hence S keep increasing, the reason for which is discussed in detail in part 1b of this video series. The forthcoming part 1b continues to consider the other important aspects of energy level distribution of particles and the resulting thermal entropy, including the use of Bottzmann distribution calculations and the resulting W's and hence S's to illustrate the working of the second law of thermodynamics at the microscopic level of particles.